Okay, so now let's talk about the basically permutations when all objects are distinct. And what that means is that for example, when you have in the previous example where we had the word, for example, the word rose, we have all of these letters, these 4 letters related to the word rose, and for example, we wanted to know how many 4-letter words we could make with the 4 letters of the words of the word rose. And basically what we found out was that basically the number of words that we could make with the number of 4-letter words that we could make with the letters of the word rose, provided that we don't repeat anything, was basically 24 words. Right? Now, over here what happens is that basically, as you can see, we said that basically permutation is the different arrangements of different objects, taken basically all of them or some of them at a time, meaning that for example you have a number of objects, like for example the letters R, you have the letter O, you have the letter S, and you have the letter E, right? So you have these 4 letters, these are your objects. And permutation, what that means is that permutation is the different types of the different arrangements of these 4 letters, which are basically your objects, taking some of them, or basically all of them at a time. For example, taking some of them would be making, for example, 3-letter words using these 4 letters, or using 2-letter words using these letters, or and when you take all of them at a time, that means that you take basically the 4 of them at a time, and then basically you create 4-letter words. So that's basically that. And there is situations where the objects that you use are distinct, meaning that for example the 4 letters that you use here are O, S, and E, of course, these are distinct. These are distinct letters. Or for example, if you use, for example, 4 different school bags. So 4 different school bags, for example, you would denote them as B1, you could B2 and B3 and D4. And of course, again, these would be distinct objects. On the other hand, you could have 4 objects. For example, you couldn't say that you would have 4 objects. You could have, for example, 3 school bags. For example, B1, B2, and B3, right? You could have 3 school bags, but then I want to basically find out all the different permutations of these school bags, provided that I take my objects, for example, as for example B1, B2, for example B3, and again for example B1 over here. So then basically in this example, our objects are not distinct, meaning that basically B1 has been repeated 1 time. So now in this case, what we want to consider is basically the permutations when all the objects are distinct. For example, the permutation of these 4 letters, for example, taken all or some at a time. So that's basically what we are interested in right now. So the permutations, permutations when all objects are distinct. So as a theorem, or theorem number 1 to be more exact, as theorem number 1. Okay, so basically then theorem number 1, I was doing a couple of things over here. As theorem number 1, what we have here is the number of permutations of n different objects taken r at a time, where r is greater than 0 and less than or equal to n, and the objects do not repeat, is basically n times n minus 1 times n minus 2 all the way up to n minus r plus 1. So the number of the permutations of n different objects taken r at a time, where 0 is less than r, less than or equal to n, meaning that r is greater than 0 and less than or equal to n, because if your r is 0, then of course you have no permutations and there is no point in calculating the permutations, because for example then you would be calculating the number of different zero letter words, for example, that which can be made, for example, with the 4 letters, for example, the 4 letters, for example, ROSE. Of course, you know that the number is 0 already. So basically, there is no need to calculate that. So what that means is that then the number of permutations of n different objects taken r at a time, where 0 is less than r, less than or equal to n, and the objects do not repeat, is basically n times n minus 1 times n minus 2 times all the way up to n minus r, n minus r minus 1, basically n minus r minus 1, which you can write as n times n minus 1 times n minus 2 times all the way up to n minus r plus 1. N minus r plus 1. So, and the way that you can get to this, of course, it's easy, meaning that of course, when you had, for example, 4 letters, for example, ROSE, and you wanted to calculate the number of 4-letter words that can be made using these 4 letters, that would be, for example, 4 objects taken, for example, 4 at a time, which would be, for example, all of these 4-letter words, which would be, for example, in this case, you could fill this placeholder in 4 different ways, 3 different ways, 2 different ways, and one way. So that the total number of the words that could be made in such a way would be basically 4 times 3 times 2 times 1, which whatever that is not important right now. And then, for example, if you have the same number of objects, but you want to, using the same number of objects, you want to create 3-letter words. So that would be then 4 objects taken, for example, taken 3 at a time. 3 at a time. Which would be basically, you have 3-letter words, so you have 4 ways of filling this placeholder, 3 ways and 2 ways, so that the total number of the different words that you can make would be 4 times 3 times 2. Again, if you have basically the same 4 objects and now using those 4 letters you want to make 2-letter words, then that would be, for example, 4 objects taken, for example, taken 2 at a time, which would be basically, for example, 4 ways to fill this placeholder, 3 ways to fill this placeholder, so that would be 4 times 3. And if you have the same 4 objects, and if you want to, using those 4 objects, you want to make 1-letter words. So that means basically taken 1 at a time. That would be basically only 4 ways of filling just one placeholder, so that would be only 4. So as you can see, in all of these cases, 0 is less than r, less than or equal to n. N is always basically less than or equal to r, or r is always less than or equal to n, and r is always greater than 0. And so, for example, this product, you can write it as, and over here your n is equal to 4 and your r is equal to 4, right? Over here your n is equal to 4, your r is equal to 3. Over here your n is equal to 4 and your r is equal to 2. And over here your n is equal to 4 and your r is equal to 1. And so what that means is that then basically these numbers, I can write them as n times n minus 1 times n minus 2 times n minus 3. And over here I can write these numbers as n times n minus 1 times n minus 2. And over here I can write these numbers as n times, for example, n minus 1. And these numbers I can write them as n. So, and with respect to r, I can write these as basically n times, I can write these as n times n minus 1 times n minus 2 all the way up to n minus r minus 1. Because here r is equal to basically 4, so 4 minus 1 is equal to 3, that would be n minus 3, which is the last term here. And again over here I can write n times n minus 1 times n minus 2 all the way up to n minus r minus 1, which is basically r here is equal to 3, so 3 minus 1 is equal to 2, so that's n minus 2, which is the last term here. And again I can do the same thing here, for example, n times n minus 1 all the way up to n minus r minus 1, and over here you can see that r is equal to 2, so 2 minus 1 is equal to 1, so n minus 1 is again the last term here, and the same thing keeps going again and again. So you can write all of these, so you can write basically the number of permutations, so you can write the number of permutations the number of permutations of n different objects taken R at the time, where 0 is less than R less than or equal to n, and the objects do not repeat, is basically, you can write it as this thing over here, which is n times n minus 1 times n minus 2 times all the way up to n minus r minus 1, which is the same thing as n times n minus 1 times n minus 2 times n minus r plus 1. n minus r plus 1. So that's basically the theorem number 1. Now this theorem can be proved, and we will prove it. Okay, so now basically the proof here is pretty simple. The proof is there will be as many permutations. The proof is there will be as many permutations of there will be as many permutations as there are ways of filling n vacant places by n objects. The first place can be filled in n ways. So the first place can be filled by in n ways, or basically in n ways, following which the second place can be filled in n minus 1 ways, following which the second place can be filled in n minus 1 ways. Following which the third place can be filled in n minus 2 ways. Following which the third place can be filled in n minus 2 ways. And you can just keep going, and so that means that following which the rth place can be filled in n minus r minus 1 ways. n minus r minus 1 ways. Therefore, the number of ways of filling in r vacant places in succession is, therefore the number of the number of ways of filling in the number of ways of filling in R vacant places in succession is n times n minus 1 times n minus 2 all the way up to basically n minus r, or r minus 1, I'm sorry, r minus 1, or basically you can write that as n times n minus 1 times n minus 2 times all the way up to n minus r plus 1. This expression for n permutation r is cumbersome, and we need and of course this would be denoted as n permutation r, which means that which is basically the same thing that we talked about, all the different ways of filling in basically n of all the ways of filling in r vacant places with n objects. Or you can say that n taken r at a time. The permutation of that would be basically n times n minus 1 times n minus 2 all the way up to n minus r plus 1. Now, of course, there is a problem with this notation, and that is basically when the number of these terms grows larger and larger, then you have to just keep basically subtracting and multiplying and so on and so forth. So it's not going to be very easy to deal with this notation. And so the symbol n factorial, we can use this the factorial notation. So we can use the factorial notation to simplify the formula above. And so that's basically the whole, that was basically the definition, and also the basically theorem 1, which basically calculates n permutation r. Now let's go over to let's learn a couple of things about the factorial notation as well, so that we can simplify this thing. So the notation n factorial, read as basically n factorial. So that represents the product of first n natural numbers. This represents the product of the first n natural numbers. The product of the first n natural numbers. That is the product 1 times 2 times 3 times all the way up to n. And of course you can write it as times, for example, n minus 1 times n. So that basically means that this product is equal to n factorial. So what that means is that then basically 1 factorial would be equal to 1. 2 factorial would be equal to 1 times 2. 3 factorial would be equal to 1 times 2 times 3. 4 factorial would be equal to 1 times 2 times 3 times 4. And so on and so forth. And we define 0 factorial as 1. This is a definition. This is a definition, and so we define 0 factorial as 1. And of course, by that notation, or by that logic, you know that you can say that for example 5, you can write 5 factorial as basically, you can write it as 1 times 2 times 3 times 4 times 5, which is the same thing as, this is the same thing as 4 factorial. So you can write this as 4 factorial times 5. Or for example, you can write this as, for example, you can think of this as 3 factorial. So then you can write this as, for example, 3 factorial times 4 times 5. Or you can write it as 2 factorial times 3 times 4 times 5. Or you can write it as 1 factorial times 2 times 3 times 4 times 5. And of course, for a natural number n, and for any natural number n, n factorial is equal to n times n minus 1 factorial. Because as you saw over here, for example, 5 factorial, I could write it as 5 times, for example, 4 factorial. So this is n times n minus 1 factorial. So n factorial can be written as n times n minus 1 factorial, which is the same thing as, which you can write as, and then again n minus 1 factorial, you can write it as, for example, n minus 2 factorial, n minus 1. So n minus 1 factorial, you can write it as n minus 2 factorial, times n minus 1. So then I can write this as n times n minus 1, n times n minus 1 times n minus 2 factorial. And you can just keep going by the same logic. You can write this as, for example, you can write it as n times n minus 1 times n minus 2 times n minus 3 times n minus 3 factorial. That you can do as well. Of course, this is provided that n is greater than or equal to 0. This is provided that, for example, provided that n is greater than or equal to 0. Or here, this is provided that basically n is greater than or equal to 2, and so on and so forth. And you can, of course, continue with this in the same way. And well, as an example, let's say that, for example, you want to evaluate, for example, 5 factorial. So to evaluate 5 factorial, you have the same, it's basically 1 times 2 times 3 times 4 times 5, which is equal to, well, that's 20 times, for example, 6, which is equal to 120. Or 7 factorial, for example, would be 1 times 2 times 3 times 4 times 5 times 6 times 7, which is the same thing as, for example, 42 times 20, which is equal to 820. 820 times 6 is equal to 0 and 12, 1, 48, 49, so that's 4920. That's what it seems that it's 5040. Let's see. It seems that it is basically 20 times 6 is equal to 20 times 6 is equal to 120, and then 120 times 42. 42 times 12 is 0 over here. That's it. That's 48. 0, 42, and then you have 8, and this is a 6, 4, 6, 8, 0. One times 2 times 3 times 4 times 5 times 6 times 7. 1 times 2 times 3 times 4 times 5 times 6. 6 times 7 is equal to 42. 5 times 4 is equal to 20. And 3 times 2 is equal to 6. 6 times 2 is equal to 12. That's 120. 120. So 12 times 42 with a 0 is, I don't understand. That is 84. 2 times 40 is equal to 84. 0 and 42. So you have 4, 0, and 5. That is actually correct. That is 5040. So that is that. And for example, 7 factorial minus 5 factorial. 7 factorial minus 5 factorial is equal to, for example, 5040 minus, for example, 120, which is 4,900 and 4,900, and then over there you have a 20, so 4,920. So that is that. And suppose that, for example, you want to calculate, for example, 7 factorial by 5 factorial. 7 factorial by 5 factorial. You can write this as, for example, 5 factorial times 6 times 7. You can write this as 5 factorial times 6 times 7 and 5 factorial here. You can simplify these two and get 42. Or you can, or if you have, for example, 12 factorial over 10 factorial times, for example, 2 factorial, you can write this as, for example, 10 factorial times 11 times 12 over 10 factorial, and 2 factorial is just 2. So then you can simplify these two, and that would be 6, so that would be 66, for example. And if you have, for example, something like, for example, n factorial over r factorial times n minus r factorial, n factorial over r factorial times n minus r factorial. So let's see what that is. We want to evaluate this when n is equal to 5. You want to evaluate this when n is equal to 5 and r is equal to 2. And r is equal to 2. Okay, so to calculate, for example, n factorial over r factorial times n minus r factorial when n is equal to 5 and r is equal to 2. So what you can do is that, of course, well, this is going to be equal to then 5 factorial over 2 factorial times, for example, 3 factorial, which is the same thing as, for example, 3 factorial times 4 times 5, 2 times 3 factorial, and then you can simplify these, and then simplify these and you will get a 10, for example. Or for example, if you have 1 over 8 factorial plus 1 over 9 factorial, for example, let's say you have an equation 1 over 8 factorial plus 1 over 9 factorial is the same thing as x over 10 factorial. So what you can do is that you can write this as 8, basically 7 factorial times 8, for example. Or you can write this as 8 factorial times 9. So that's 1 over 8 factorial plus this is 1 over 8 factorial times 9. And then you can write this as, for example, x over 10 factorial. And then that would be equal to, for example, and I can do this as well, meaning that I can write this as, for example, x over 8 factorial times 9 times 10, and then take a 1 over 8 factorial out. So 1 over 8 factorial, take it out, that would be 1 plus, for example, 1/9 is equal to, for example, 1 over 8 factorial times x over 90, and then I could simplify these two together, and then I could basically take this, write this as, for example, 9 plus 1 is equal to x over 90, simplify these, and then that would be 10 is equal to x over 10, so x is equal to 100. X is equal to 100. Now let's do a couple of exercises as well. Let's see what we have here. So for example, I don't know, you want to evaluate, for example, 8 factorial. It's simple. It's 1 to 1. So 8 factorial would be 1 times 2 times 3 times all the way up to 8. Or basically, for example, 4 factorial minus 3 factorial. You can write it as 3 factorial times 4 minus 3 factorial, which is equal to 3 factorial times 4 minus 1, which is equal to 3 times 3 factorial. 3 times 3 factorial, which is equal to 3 times 6, which is equal to 18. So this is number 7.2, 7.2, number this was number 1, 2, so that's 18. Okay, and then for example, question number 2, you want to know whether 3 factorial plus 4 factorial is it equal to 7 factorial. 3 factorial plus 4 factorial is it equal to 7 factorial. So you know that basically 3 factorial is, you can write this as 3 factorial, your LHS is equal to 3 factorial plus 3 factorial times 4, which is equal to 3 factorial times 1 plus 4, which is the same thing as 5 times 3 factorial, which is equal to 5 times 6, which is equal to 5 times 6 is equal to 30. Now 7 factorial is, of course, much larger than 30. So your RHS is basically 1 times 2 times 3 times 4 times 5 times 6 times 7. And that's equal to basically 42 times 20 times 6, which is equal to 120. So I can write that as 42 times 12 with a 0. And then you have 84, a 0, and 42. So you have 4. And you have basically a 0 here and a 5. So that's 5040. And as you can see, basically your LHS is not equal to RHS, which means that basically 3 factorial plus 4 factorial is not equal to 7 factorial. So that is that. And then, for example, let's say you want to compute 8 factorial over 6 factorial times 2 factorial. You have 8 factorial over 6 factorial times 2 factorial, which is equal to basically 6 factorial times 7 times 8. And over here you have 6 factorial, for example, 2 factorial is just 2, so 6, and these you can, 4 times 7 is equal to 28. So number 3 is 28. And number 4 is you want to find x in an equation involving factorial, or the factorial notation. So let me open my window. Okay, so you have 1 over 6 factorial, for example. You have 1 over 6 factorial plus 1 over 7 factorial is equal to, for example, x over 8 factorial. So you can rewrite this as 1 over 6 factorial plus 1 over 6 factorial times 7, and then over here you can write this as x over basically 6 factorial times 7 times 8. X over 6 factorial times 7 times 8. And so here I can take 1 over 6 factorial out, and then I would have 1 plus 1/7 is equal to basically 1 over 6 factorial times x over 7 times 8. And then I can simplify these two. Now I can write this as a 7, so 7 plus 1 is equal to x over 7 times 8. And so this is 8 over 8/7 is equal to x over 7 times 8. And so 8, and of course you cannot simplify this that way. You cannot simplify this that way, but what you can do is that simplify 7 and 7 in the denominator, and so your x is equal to 8 times 8, which is equal to 64. So number 4 is 64. Number 5, we want to evaluate some expression . 459, 460. We want to evaluate some expression which is, for example, n factorial over n minus r factorial when, for example, when n is equal to 6 and, for example, r is equal to 2. It's pretty simple. So this would be equal to 6 factorial over 4 factorial, which is equal to basically 4 factorial times 5 times 6 over 4 factorial, and then that's equal to 30, for example. Or basically again the same thing, n factorial over n minus r factorial, when n is equal to, for example, 9 and r is equal to 5, would be equal to 9 factorial and 4 over 4 factorial, which is equal to 4 factorial times 5 times 6 times 7 times 8 times 9, and divide that by 4 factorial. Simplify these to get 30 times 72 times 7. So that's 30 times 7 is equal to 210. 210 times 72, 9 times 8, so 21 times 72 with a 0. You will get 42 0, and then 7 and 14, and then you have 2, 11, 1, 5, 1, and you get, so that's basically 15,120. 15,120, that was number 5. 30 and 15,120. Okay, so the next thing that we have is the derivation of the formula of n permutation r. Now that basically we understand the factorial notation, we can use it in order to derive the formula for n permutation r. So previously we said that n permutation r was equal to n times n minus 1 times n minus 2 times all the way up to n minus r minus 1, which is equal to basically which is equal to n times n minus 1 times n minus 2 times all the way up to n minus r plus 1. Now, that is n permutation r, right? Now, multiplying the numerator and denominator by n minus r times n minus r minus 1. Now, if you basically multiplying the numerator and denominator, by n minus r times n minus r minus 1 times all the way up to 3 times 2 times 1. So basically over here you have you go all the way up to n minus r minus 1, n minus r minus 1, and n minus r. You see this n permutation r goes from n minus r plus 1, right? It goes from n minus r plus 1 all the way up to n. So basically you can think of this as n minus r plus 1, and that goes all the way up to n, right? Now n minus now the next term over here would be for example, you could calculate this as for example, if you have, suppose that this is n minus r minus 1, then the next term would be basically the next term would be n minus r minus 0, right? Because as you're going towards these see over here what happens is that basically over here what happens is that as you, for example, write, we said that basically as we write, for example, 4 permutation 4, right? That was basically the same thing as 4 times 3 times 2 times 1. 4 permutation 3 was the same thing as 4 times 3 times 2. 4 permutation 2 was the same thing as 4 times 3, and 4 permutation 1 was the same thing as 4. Now, as you can see, now over here your n is equal to 4 and your r is equal to 4. Over here your n is equal to 4 and your r is equal to 3. Over here your n is equal to 4 and your r is equal to 2, and so on and so forth. So you can see that this last term over here, this is basically n minus, so over here basically this is n minus so this would be n minus r minus 1, right? In every case, this last term could be represented by n minus r minus 1. N minus r minus 1. Which would be, of course, n minus r plus 1, as you can see here, right? So what that means is that when I want to get basically a number 1 larger than this number, I have to increase this number by, or I have to decrease this number by 1, meaning that then basically n minus r, to decrease this number by 1, I would have to basically subtract a 1 from this number, which would be n minus r minus 1 minus 1, which would be the same thing as n minus r, for example, minus 2, right? Now if I use this expression here, so in this case, for example, n minus r minus 1 would be, so basically r minus 1 here is equal to 3. So then 4 minus 3 is equal to 1. And then this term would be n minus r minus 2, because n minus 2 here is equal to, or I'm sorry, r minus 2 is equal to 2, and 2 minus 2 is equal to 2. So as you can see, this term over here can be represented by n minus r minus 1, and this term over here can be represented by n minus r minus 2. And by the same logic, I have to, again, to get to this term, for example, I have to decrease this number by 1, meaning that this number would be represented by n minus r minus 3, and so on and so forth. So what that means is that basically in this now my goal here is to represent this by to rewrite this expression and basically somehow basically express it in terms of the factorial, basically notation. So how I can do that is that, of course, I know that n permutation r. I know that n permutation r is equal to basically n times n minus 1 times n minus 2 times all the way up to n minus r minus 1, right? Now, you know that anything factorial, for example, n factorial, is the same thing as basically 1 times 2 times 3 times all the way up to n, meaning that your product has to start from 1 and go all the way up to n, and that would be called n factorial, and there you could use the factorial notation. Now I need to kind of do the same thing over here, so that I can use the factorial notation to rewrite this expression. And that's basically why they're multiplying the numerator and the denominator by this expression, and we will basically derive this exact expression on our own in just a few moments. Okay, so now what that means is that basically if I have this expression over here, and if I want to write it in factorial notation, what I need to do is that I need to write it all the way from 1 to n, basically. There is no other way. And then somehow hope that, for example, the rest of the terms will simplify in the numerator, and then somehow get some expression in terms of, for example, n factorial or something like that. So what I need to do is basically the terms that I need that would basically make this a complete factorial expression, I would need to add to it, right? So I can now this expression has been written the other way around, meaning that normally when you have n factorial, you start from 1 and go to 2, 3, 4, and all the way up to n, right? And so over here, for example, you have for example n, and then you have times n minus 1, you have times n minus 2, and so on and so forth, right? So that's basically how you normally have these expressions. So now, as you can see, this expression has started with n. Of course, it doesn't really make any difference because all of these terms are multiplied together. So whether you write it this way or this way, it doesn't make much difference, or any difference for that matter. But since I want to figure out what I need to add to this expression, I'm going to write it the other way around, meaning that I'm going to write n permutation r as, of course, I start from, this seems to be the smallest value basically over here multiplied by all the other terms. So I write it as, for example, n minus r minus 1, and I multiply this by all of these terms, and then as you can see, it goes to n minus 2 times n minus 1 times n. Now there are basically all of these terms that have to start from 1, and I have to go to 2 and 3 and all the way up to the term that comes exactly before this, right? And the way to figure out this term is basically, we said that over here, each time we had to, basically we said that over here, as you saw. So for example, as I was getting away from, or basically getting away from 1, this was n minus r minus 1. This was n minus n minus r minus 2, n minus r minus 3, and so on and so forth. Meaning that as I move to the next number, for example, from 2 to 3, you have to take this number and subtract a 1 from this part, meaning that r minus 2 minus 1 would be r minus 3, or r minus 1 minus 1 would be r minus 2, and so on and so forth. So now over here I'm doing the same thing, meaning that I'm getting away from 1, and so as I do so, I have to basically take this r minus 1 and basically subtract a 1 from it, meaning that what that means is that the term that came before this was actually n minus r, right? This was n minus r, and then of course if I to get to the next term, I have to basically take this r and subtract a 1 from it, which would be basically n minus r minus 1, or n minus r minus 1, which would be this term over here. So it seems that if I multiply this expression, if I add all of these terms in the beginning, I will have basically n factorial in the, I can write this expression as n factorial. So what I'm going to do is that I'm going to write this as 1 times 2 times 3 times all the way up to n minus r. And I remember that I need to remember that basically I have basically multiplied this expression, which was originally basically this thing over here, from here all the way up to here. I have multiplied it by all of these numbers. So since I have done so, and since I don't want to change the value of n permutation r, I'm going to take this and divide it by the same thing, meaning that 1 times 2 times 3 times all the way up to n minus r. And and I think that's the same thing that, or at least I hope that that's the same thing that we have here. So and then this is actually exactly the same thing that we have here, meaning that here we said that we multiply both the numerator and denominator by 1 times 2 times 3 times all the way up to n minus r. And of course, as you get closer to 1, you have to of course add a 1 to basically r, which would be basically, for example, if you had n minus r here, and if you were to add a 1 to r, you would get basically n minus r plus 1, which would be n minus r minus 1, which is this thing over here. So that's exactly what we have found, right? Now what I need to do, so basically I can write this as n minus r minus, basically n minus r over here, n minus r minus 1. I can write this term as well, n minus r minus 1, and over here I can write, for example, I can write the n minus r minus 1 over here as well. I can write the n minus r minus 1 over here as well, and that is times all of these things over here. So that's basically that is basically now if you pay attention to this expression basically then your numerator, excuse me. Okay, so now I got a phone call, so I have to stop this video. So now basically, now as you can see, this expression up here is actually nothing but n factorial, because, well, what we did was that basically we figured we actually figured out all the terms that were missing, starting from basically all the way up to this term over here that we already had, and then we multiplied all of those terms by the original terms that we had. So then naturally this is going to be n factorial, because n factorial is nothing but 1 times 2 times 3 times all the way up to, for example, n minus 1 times, for example, n, and that is the same thing as n factorial. Now, in case this part over here, of course, this basically your numbers start from 1 and go all the way up to n, and before n you have n minus 1, and then before that you have n minus 2, so there is no problem with that. There is no problem with here. But in case these three terms in the middle are kind of confusing, you can, for example, think of r as some number less than or equal to n and greater than 0, because you know that r is less than or equal to n and it's greater than 0. So, for example, you can imagine that r is equal to 4, for example, right? Let's say that r is equal to 4. So if r is equal to 4, then this term over here would be n minus r, this term over here would be n minus 4. And then this term over here would be n minus, n minus r minus 1, which is n minus r plus 1, right? N minus r plus 1, which is the same thing as, for example, something like, for example, n minus 4 plus 1. And then all of these terms basically go all the way up to n over here. And of course you have those two, but that we have already understood. And that is basically n minus, for example, this thing over here is n minus 4, for example, minus 1. And this is plus 1. And then this goes all the way up to 1 times 2 times 3, and so on and so forth. So if I rewrite this, I will get 1 times 2 times 3, and this is n minus 4. And this is... of course, as you get closer and closer to n, this is n minus 3, and then of course it makes sense that over here you would have, for example, n minus 1, and then you would have n minus 2, and then you would have n minus 3, and so on and so forth. So n minus 2, n minus 3, so n minus 3, n minus 4. So this is actually, there is nothing wrong with that. I mean, everything is absolutely correct. And then over here you have n minus 5, and you go all the way up to 1, 2, 3, and this way you go all the way up to n. And so that means that basically this is simply n factorial. So then that means that basically then your numerator is n factorial, and your denominator is just simply n minus r factorial, because because you have all the numbers starting from 1 times 2 times 3 times all the way up to basically n minus r minus 1, and over here you have n minus r, meaning that you have basically, well, 1 times 2 times 3 all the way up to n minus r, so that's n minus r factorial. And that is basically, that is the n permutation r. Now in case, of course, the factorial notation, and in the beginning it's a little bit tricky to work with it, but it's super important in series and basically infinite series and that sort of thing. And so you do need to understand how to work with the factorial notation and how to simplify it and do different operations on it, but we will get enough exercise there, so you will be good to go. So that's basically n permutation r, which is n factorial over n minus r factorial. And to basically to remember or to understand what this thing is basically very simply, it's basically all the arrangements. You can think of this as basically all the, or the, you could say the number of all the different arrangements of basically n distinct objects, and distinct objects taken r at a time, where basically where 0 is less than r is less than or equal to n, meaning that r can be actually equal to n. And in case you do need a practical or you do need an example to remember this, what you can remember basically here is that you have basically the letters of the word rows, and you want to know, you want to use the letters of the word rows, for example, the example that we already had. So you want to use the letters of the word rows in order to make as many basically, for example, for instance, 4-letter words as possible, keeping in mind that repetition is not allowed. What that means is that basically you take the letters of the word rows, R-O-S-E, for example, and you want to make these 4-letter words. So that means that you have one placeholder here, another placeholder, another placeholder, and another placeholder for the 4 digits. And so since you have 4 letters here, then of course you would be able to fill this placeholder with 4 different letters. So there are 4 different ways of filling this placeholder. Now, since repetition is not allowed, then of course you have already used one of the letters here, then there are another 3 ways to fill this placeholder. After that, you would have 2 different ways of filling this placeholder. And after that, there is only 1 way to fill this placeholder. And then all the different such words that you would get as a result of this experiment, I could call it, would be based on the fundamental principle of I do forget this thing, principle of counting, based on the fundamental principle of counting. You would have basically 4 times 3 times 2 times 1 words, which would be basically, for example, 24 words, which would be 24 words. Now these 24 words are and now basically, so in this experiment that we did, we had 4 objects. And using these 4 objects, we had 4 letters over here. We had 4 letters here, and using these 4 letters, we made 4 letter words, right? So this situation is in the language of permutation and combination and that sort of thing. This situation is usually described as basically 4 objects. We refer to these letters, for example, as objects collectively. 4 objects taken 4 at a time. Or to more generally, you can say the same thing as n objects taken r at a time. And now you can of course use the formula to calculate the same thing over here. So basically, using simple calculation, we got basically a 24. And if you use the formula that we found that n permutation r was 24. So now over here, my n was equal to 4 and my r was equal to 4. So then 4 permutation 4 would be equal to n factorial, which is 4 factorial, over n minus r factorial. So n permutation r is equal to basically n factorial over n minus r factorial, which is equal to 4 minus 4, which is 0 factorial, and 0 factorial is equal to 1. And 4 factorial is the same thing as 4 times 3 times 2 times 1, which is, as you can see, is the same thing that we used over here, right? So which is equal to 24. So if you remember this situation of the word rows and basically the whole thing that we did before we derived this formula and the whole story, then you will never actually forget the concept of permutation, and of course you might probably sometime, if you don't use this formula for a long time, you might forget this thing, but the concept of permutation, of course, you will never forget it if you remember it, using for example, the example rows that we talked about before. Okay, so that was basically that. And now there is a couple of things that we need to discuss here, and then we have basically another theorem which is a little bit different from this, but let's finish this one and then we will get to the next one. Okay, so now the formula that we found for the concept of basically permutation is basically n permutation r is equal to basically n factorial over n minus r factorial, where basically 0 is less than r less than or equal to n. Of course, you can see that over here r cannot be equal to 0, and that's important to note. And but I don't like mosquitoes. It seems that okay, so that is basically, I mean, so far so good, we have no problem. And when r is equal to n, we have basically n permutation n is equal to n factorial over n minus n factorial, which is equal to basically n factorial over 0 factorial, which is equal to n factorial over 1, which is equal to n factorial. So when r is equal to n, then basically n combination n, of course, is equal to n factorial. And what that means is that you have for example 4 letters. You have 4 letters, for example ROSE, and you want to know how many 4-letter words you can build with this. You can build with these 4 letters, and so of course it would be equal to 4 times 3 times 2 times 1. So over here your n is equal to 4, and this is basically 4 times 3 times 2 times 1, which is equal to 4 factorial. This is 4 factorial, which is of course equal to n factorial, as you can see here. Or you can say that basically when n is equal to r, that means that you have basically, you can say n objects taken n at a time. You have n objects taken n at a time. Okay, so that is basically that. And now the next thing that we have here is counting permutations is merely counting the number of ways in which some or all objects at a time are rearranged. So counting permutations is merely counting the number of ways in which some or all objects at a time are rearranged. Arranging no object at a time at all is the same as leaving behind all the objects, and we know that there is only one way of doing so. Thus we can say that n permutation 0 is equal to 1, which is equal to n factorial by n factorial, which is equal to n factorial over n minus 0 factorial. So there is a there is a case over here where you say, where we have basically, it says that counting permutation is merely basically counting the number of ways in which some objects, in which all objects, in which some or all objects at a time can be rearranged. And arranging no objects at all, meaning that when you have n combination 0, or arranging no objects at all, is the same thing as, so this is arranging no objects at all is the same thing as leaving all, basically it's the same thing as leaving behind all the objects, leaving behind all the objects. Okay, and we know that, and there is only one way of doing so, and there is only one way of doing so. I mean, there is only, what that means is that there is only one way of leaving behind all the objects. You just leave behind all the objects. And we know that there is only one way of doing so. Therefore, we have n. This is actually supposed to be p. So we have n permutation 0 is the same thing as basically n factorial over n minus 0 factorial, which is the same thing as n factorial by n factorial, which is equal to 1, right? So that's the meaning of basically n permutation 0. And so that means that r can be equal to 0 as well. And so we can say that then this formula is applicable for r is equal to 0 as well, meaning that I can write n permutation r is the same thing as n factorial over n minus r factorial, where 0 is less than or equal to r, less than or equal to n. So I added the equal sign over here. And that's the end of this part. Now there is another theorem here. I think we should do this one here in this video as well, and then we will end this video. So theorem number 2 is the number of permutations of n different objects taken r at a time where repetition is allowed. Okay, so theorem number 2 is the number of permutations, the number of permutations of n different objects, different objects taken r at a time, where repetition is allowed, is basically n raised to the power r, meaning that basically, for example, let's say that, for example, you have the letters of the word rose, and you want to, out of these letters, you want to basically build 4-letter words where repetition is allowed. So of course over here there are 4 ways of filling this placeholder. Now this placeholder can be again filled with 4 different ways. This placeholder can be filled with 4 different ways, and this placeholder as well can be filled with 4 different ways. So then by the principle of by the fundamental principle of counting, then by the fundamental principle of counting, the number of permutations here would be 4 times 4 times 4 times 4, which is 4 raised to the power 4. Now if, for example, if you had the same number of letters over here, n is equal to 4, and out of these you wanted to build 3-letter words, then you would have 4 ways of filling this, and of course over here repetition is allowed. Of course, repetition is allowed, right? So what that means is that, again, you have the same situation, n is equal to 4, and then out of these letters you want to build 3-letter words. So 3-letter words would be basically 4 ways of filling this place value, 4 ways of filling this place value, and 4 ways of filling this place value, which is going to be equal to 4 times 4 times 4, which is equal to 4 raised to the power 3. So then that means that you will come up with the expression n raised to the power r. N raised to the power r is basically the permutation of n different objects taken r at a time where repetition is allowed. And the proof is very similar to that of theorem 1 and is left for the reader to arrive at. Here we are solving some of the problems of the previous section using the formula for n permutation r to illustrate its usefulness. So for example, in example number 1, I think I did something. Okay, so now let's use these formulas to solve the problems that we had before. And basically, for example, we have example number 1, and we have let me take a look at example number 1. Let me see what that was. Example number 1. So example number 1 was the exact example that we had before. The rows, the word, you wanted to find the number of 4-letter words. You wanted to find the number of 4-letter words. 4-letter words with or without meaning. With or without meaning. With or without meaning, which can be formed out of the letters of the word rows. Which can be formed out of the letters of the word rows, where repetition of the letters is not allowed. And repetition is not allowed. Okay, so over here, basically the required number of words would be basically, you are making 4-letter words, so your r is equal to 4, and you're making those 4-letter words using the letters of the word rows. So that means that over here your n is equal to 4. So your n is equal to 4, your r is equal to 4. So we said that n permutation r is equal to basically n factorial over n minus r factorial. So then basically you can say that 4 permutation 4 is the same thing as basically 4 factorial over 4 minus 4 factorial, which is equal to 4 factorial over 0 factorial, which is equal to basically 4 factorial over 1, which is equal to 4 times 3 times 2 times 1, which is equal to 24, the same number that we got before. And if the repetition is allowed, the required number of words would be, of course, now provided that repetition is allowed, the number of permutations would of course be basically n raised to the power r, which would be basically 4 raised to the power 4, which is equal to 256. And for example, if you want to calculate, for example, the number of 3-letter words which can be formed by the letters of the word number, again we can calculate that as well. Okay, so for example, if you want to now suppose that you want to calculate the number of 3-letter words, the number of 3-letter words that can be formed by the letters of the word, that can be formed by the letters of the word number, for example, right? So that would be, for example, you see over here the letters of the word number is basically, you have six letters here, meaning that n is equal to 6 here. And since you're making 3-letter words, then you're basically, what you're doing is that you have basically 6 objects, and taking basically 3 at a time, which would be basically 6 permutation basically 3, which is the same thing as 6 factorial over 6 minus 3 factorial, which is the same thing as basically 3 factorial times 4 times 5 times 6 over 3 factorial, which is the same thing as 120, right? And of course, in this case, I suppose you know that repetition is not allowed. Now if repetition here is allowed, now if in this example repetition is allowed, we would have basically the number of words would be equal to n raised to the power r, n raised to the power r, which would be basically 6 raised to the power 3, which is equal to, I don't know, 36 times 6 is equal to 36, 3, 18, 21, 216. 216, right? And as another example, the number of ways in which a chairman and a vice chairman can be chosen from amongst a group of 12 persons, assuming that one person cannot hold more than one position. So the number of ways, for example, the number of ways in which a chairman and a vice chairman can be chosen from amongst a group of 12 people. Can be chosen from amongst a group of 12 people. 12 people, assuming that one person cannot hold more than one position. One person cannot hold more than one position. So the number of ways that you can do that, so the number of ways would be the number of ways that you can do that would be basically you're basically selecting 2 people from among 12 people. So that would be 12 permutation 2, and in the definition of permutation, basically in the definition of this formula, which is basically we have n permutation r, we have basically n factorial over n minus r factorial. In the definition of this formula, we already have assumed that repetition is not allowed. If that was not the case, then we would simply write, for example, we would simply write those number of ways as basically n raised to the power r, for example, right? So that's basically the 2 ways here. Basically repetition is allowed, right? Okay, so then, and the assumption that we have made here that repetition is not allowed, that is basically the exact same thing that has been assumed here, meaning that here we are assuming that one person cannot hold more than one position, meaning that if you choose that person for one position, then you cannot again choose it for another position, which means that you should use basically this formula and not this one. So then what you need to do here is that So then what you need to do here is that you can write 12 permutation. 12 is equal to basically n factorial, which is 12 factorial over 12 minus 2 factorial, which is equal to basically 10 factorial times 11 times 12 over 10 factorial. And again, you can simplify these two, and 11 times 12 is equal to 12 and 12, that's 132. 132. That is 132. Okay, so that's basically, that was basically all about, well, many things that we talked about. I suppose we talked about permutations when all objects are distinct, and I think we started from the very beginning of permutation and we came all the way up to this point. So in the next video we will talk about permutations when all objects are not distinct. I'll see you in the next video.